Okay, we start our lectures now. Today we will continue the discussion of uniformly accelerating reference frame. In your homework, you have a question on this particular subject. Okay, the transformation between an inertial unprimed frame and a uniformly accelerating prime frame is given by this relation in equation 11. The acceleration A in the uniformly accelerating frame is given by A prime. The inertial frame acceleration is given by A. And capital A vector is the acceleration relative, is the acceleration between the two frames. All right. So if we have a particle mass of mass m, then the forces acting on the particle observed in two different frames are related according to the expression in equation 12. Okay. You can see that it looks like in the accelerating, in order to be consistent, the force measured in or observed in the accelerating frame differs from the force observed in the inertial frame by a quantity given by minus m times the uniform acceleration, vector A, right? And we give this difference between the two forces measured in the two different frames. We give it a name, a fictitious force, and it is the force is equal. The force is proportional to the mass of the particle, and also proportional to the relative acceleration between the two frames. All right. Of course, we keep in mind that it points in the direction opposite to the uniform acceleration. All right, always opposite to the direction of the acceleration. Okay. Now this fictitious force is behaves very much like a an external gravitational force close to the Earth's surface, because it is a constant in magnitude and also uniform in direction. Right. Now, in example 1, we try to analyze the problem using two different frames. 1, inertial frame. 2, non-inertial frame. All right. So here we have a small weight of mass m hangs from a string in an automobile, which accelerates at rate a, as shown in this figure. Now, what is the static angle of the string from the vertical, and what is its tension? All right, so if we are in the inertial non-inertial frame, then this is static. The mass does not move at all. All right. However, if we are in the left frame, we see that both the car and this mass is accelerating with a in this direction. Okay. Now we shall analyze the problem both in an inertial frame and a frame accelerating with the car. Okay, in the inertial frame, we draw the force diagram of the mass m. It is attracted by the gravitational force downward is denoted by W. And also a force is exerted on the mass through the string, and this is the tension, all right? And the direction of the tension makes an angle theta with the vertical line. And this is the acceleration of the mass, all right? So we apply the Newton's second law. The horizontal direction, we have tension sine theta. This is the force in the horizontal component. This is the horizontal component of the force acting on the mass. This will impart an acceleration, a uniform acceleration A on the mass. So it is equal to ma, F equal to ma. How about the vertical component? We know that there is no motion in the vertical component. So on the right-hand side, we have 0. On the left-hand side, the net force is equal to tension times cosine theta minus the weight, all right? Then we try to combine these two equations and solve for theta as well as the tension, all right? Now, if I move if we move the W to the right-hand side and then take the quotient of the two equations, then we obtain the result that tangent theta equal to ma divided by W. Since weight is equal to mg, so the angle is equal to A over G, all right? And how about the tension? Once we obtain the angle, we can substitute it back into these expressions here and obtain the T, all right? So say for example, once we know tangent theta, then we can derive sine theta, all right, making by means of the trigonometric identities. Then T is equal to m times square root G squared plus A squared, all right? So this is the results. These are the results derived from the analysis using the inertial frame. Now, if we go to the system, try to analyze the problem in a frame accelerating with the automobile. Again, we draw the force diagram of the small mass m. Then we identify all the forces acting on the mass, all right? Now, as you can see, there's a gravitational pull pointing downward, vertically downward, and there is a tension acting on the mass, and this direction makes an angle theta with the vertical, all right? And finally, we have to add the fictitious force. Remember that the fictitious force is proportional to the mass, proportional to the acceleration, but points in opposite direction to the acceleration, all right? So the fictitious force is equal to minus ma, horizontal component, T cosine tangent times cosine theta minus W. This is the vertical component. Since the whole mass is static, is stationary, so no net force acting on the particle, all right? No net horizontal force, no net vertical force. So we have three equations here. Then we try to eliminate the fictitious force and also eliminate the tension. Then we come to the expression for the angle. Tangent theta equal to A over G again, all right? And T can be obtained in a similar way. like before. All right, so you can see that no matter which frame you try to work on, you get the same result. Okay. Now, a very important remark, from the point of view of a passenger in the accelerating frame, the fictitious force acts like a constant horizontal gravitational force. The fictitious force is constant and is proportional to the mass. Okay, so to the observer in the to the frame to the observer, there exists two components of a gravitational force. One is the fictitious force. The other one is the genuine gravitational pull towards downwards, okay, towards the Earth. And the net gravitational force is the vector sum of these two uniform forces, okay. Now I come back to this point very soon. Now here is an exercise. Consider again the car and weight on a string of example 1, but now assume that the car is at rest with the weight hanging vertically, okay? Then this car starts to move and suddenly accelerate at rate A. Here's the problem. Find the maximum angle phi through which the weight swings. Okay, that means the angular magnitude, the angular amplitude of the swinging of the mass. Okay, phi is larger than the equilibrium position. That means larger than theta, obviously. Can you tell due to the sudden acceleration? So, what is phi? Do you understand my question? The car starts at rest and then suddenly accelerate at a uniform rate, A. Then what is the maximum angle through which the weight will swing? To be honest, this question worth only 5 points in the exam, if you have finished the example. In other words, it is a short question. All right. Take your time. Now, what is the first step in analyzing this problem? What will you do when you see this question in the final exam? Draw a diagram, okay? So draw the force diagram. Now, which frame are you going to use? Okay, the accelerating frame, okay. You are in the right direction. You are in the right direction. So move on. Yes. Mm-hmm. Mm-hmm. (100°) 180° plus theta. So it's so it hit the rooftop of the car, right? So we go to the uniformly accelerating frame, draw the force diagram. Very good. Then what's next? Write down equation of motion. Solve the equation of motion. Am I right? Now, this is a very important scenario. This is an interesting scenario. When you are inside the car, what do you see? Is it a static problem anymore? No. Am I right? This is a static problem when it is at the equilibrium position. But obviously, the swinging mass cannot be in this particular position, right? So it's a dynamic problem. So you have the equation motion, and you know the initial condition. So you should be able to answer it. Am I right? I'm trying to drive you all to a very important principle in physics. Any idea? Yep. Interesting. Remember that this is a short question in the final exam. All right, now the key point is here. The key point is this remark. Okay, now pretend that inside the car is so dark, except that you can see the mask hanging from the rooftop. Okay. Now suddenly the car starts to accelerate with a uniform acceleration. As I said here, it seems that there is a net gravitational force or a new gravitational force pulling in this direction. Am I right? That's against the tension. So basically, in this example, you have a plumb line. This is the point of contact. This is the point of contact, and this is the pendulum. Am I right? Okay. Now, if it starts at the vertical position, that means in our usual example of the pendulum, that means we move the plumb line, we move the mass sideways. Am I correct? And then release it. Am I correct? So what is the maximum amplitude, angular amplitude? You at t plus, t equal to 0 plus, then we have a gravitational force in this direction. Am I right? And our position, the position of the mass is in vertical direction. Okay, so basically, if you inside the car and you don't see other things, all right? So you sort of like seeing this. This is the equilibrium position. Now you pull it sideways. What is this? This is theta, am I right? You push it sideways. And then and release it. What will happen? To the other side, what is the maximum point it will reach? Theta. Okay? So relative to the vertical, what is this angle? What is this angle? 2 theta. Am I right? So you don't have to do any calculations. Can you follow me? Vertical, it is vertical, and a t equal to 0 plus. You add an external force. Am I right? So in other words, this is the net gravitational pull. This is the equilibrium direction. Okay, I give you one minute to digest and then ask me questions. Think about it. Yeah. Thank you. Okay, can you follow now? Now you can also consider it in this way. Think about in the lab, inertial frame, all right? In the lab frame, usually we have this vertical, the gravitational force is pulling downward vertically. And then suddenly we add a component to it. What will happen? It will swing, right? Where is the, what is the direction of the new gravitational force? Slide in this direction, am I right? Okay, so when you're inside the car, you don't see any other things. What is the vertical equilibrium position? Am I right? So you just move your pendulum sideways. When you release it, it will swing. But what is the maximum amplitude? It will be theta plus theta. Give you 2 theta. Am I right? Now, if I give you a similar question in the final exam, don't waste your time in solving the equations. Okay? This is a good question in the qualifying exam for the PhD students. Short questions. Qualifying exam. And you can find this example in the book by Klapner, Introduction to Mechanics. Have you ever bought it? It is a reference book for the Introduction to Physics. No one? It is a very good book, okay? Even though it is an old one, it is an old textbook on Introduction to Mechanics. All right, the second exercise. The second exercise, a cylinder of mass m and radius r rolls without slipping on a ball plank, which is accelerated at the rate a. Okay, find the acceleration of the cylinder. Or you can consider it in this way. You are inside a car, inside the bus, which is accelerating with a uniform acceleration, and there's a cylinder rolling without slipping inside the car, inside the bus. Okay, it's just the same scenario. All right. Now, what will you do? Which frame will you pick? Which frame will you pick? Inertial frame, the left frame, or the accelerating frame? Okay, you can try whatever you want. Yes. But if you choose the correct frame, the calculations will be much simpler. No, I mean, it's a board, accelerating board. But if you don't really see the picture, you can also put it in this scenario. You're inside a bus, which is accelerating with a uniform acceleration, and there's a cylinder rolling without slipping inside the bus. Okay, the same condition. Yes, exactly, exactly, exactly. Or when you are inside the MTR, you see some Coca-Cola can rolling without slipping. You can do the analysis. So my recommendation is that you should use the accelerating frame. Okay. Hmm? Yes, it is rolling without slipping, right? Yes. Yes. Do you remember what it means by rolling without slipping? Okay. Say we are in this in the left frame. Okay, no acceleration of this constant. We can have the scenario that a cylinder rolling without slipping. Am I right? But now somehow this classroom is accelerating sideways with a uniform acceleration. So what will you do? To with a uniform acceleration, the whole classroom, or the board or plank is perhaps I should give you the figure. I should give you the figure. Okay, so this is the figure for the example for this problem. So inside in the accelerating frame, this is the force diagram on the cylinder. A fictitious force acting at the center mass. Since it is rolling without slipping, there must be a friction. Am I right? So alpha prime is the rotational acceleration in the accelerating frame, and A prime is the translational acceleration inside the accelerating frame. Okay, so how do we analyze this problem? You can see that we can actually apply all the tools that we have learned before. Am I right? The old examples we have encountered is that the fictitious force does not exist because we are using the initial frame, right? Now keep in mind that you should use the accelerating frame. Okay, don't use the left frame. So let us repeat what we will do in the case of inertial frame. All right. So this is the friction minus the fictitious force will give you the acceleration. Am I right? The force diagram. Friction minus the fictitious force will give you ma prime. All right. How about rotation? Rolling without slipping, the constraint equation. R times F, this is the rotational motion. R times F equal to minus I naught alpha prime, right? The rotational motion. Only the friction will will exert a torque. Okay. So R times F, the friction, equal to minus I naught alpha prime. Why do we have a minus sign? Because we choose the clockwise direction to be positive. Okay. Rolling without slipping, alpha prime times R is equal to A prime. Rolling without slipping. Okay. Now, if we don't have, if the accelerating frame has an acceleration equal to 0, then we go back to the ordinary, the conventional example that we are familiar with. Okay. Okay. Simplify these three equations. We can determine the A prime. Okay. We can eliminate the alpha prime using these two equations, and then combine the resultant equation with the first equation, then we get this. All right. And we know that the fictitious force is equal to ma, the magnitude equal to ma. And the moment of inertia is equal to 1/2 mr squared. All right. So the acceleration, translational acceleration of the cylinder with respect to the accelerating frame is equal to minus 2/3 of the uniform acceleration A. Okay. The acceleration measured in the left frame is equal to A prime plus A. It is equal to 1/3 of A. All right. Now, what conclusion can you draw from these two examples? What conclusions can you draw? What insights do you have? Have you got? What insights have you got? Physical insights. Say it again. Can you speak louder? Don't be shy. Eh? Okay, but a more important insights, physical insights, drawn from these two examples. No, just like the pendulum. This is dynamic, right? Yes, the Newtonian mechanics, Newton's equation motion. The form of Newton's equation motion is preserved, okay? In other words, the so-called non-inertial frame can be treated as an inertial frame as long as we add the appropriate fictitious force. Am I right? Am I correct? There's no difference. So whether we are treating a system in an accelerating frame, uniformly accelerating frame, or we treat it as an inertial frame with an added external force, they are equivalent. All right? Now, this is the so-called the principle of equivalence that you will encounter in your study of general relativity. Okay? So keep this in mind. This is a very, very important insight. So the laws of physics in a uniformly accelerating frame are identical to those in an inertial system, provided that we introduce a fictitious force on each particle. Okay? The fictitious force is indistinguishable from the force due to a uniform gravitational field. So both the gravitational force and the fictitious force are constant forces proportional to mass. All right? In local gravitational field, a free particle mass m experiences a force equal to mg. Consider the same particle in a non-inertial frame, uniformly accelerating at rate a, with no gravitational field, nor any other interaction. The apparent force is the fictitious force, which is equal to mg, right? So there's no difference. Whether you think of the system as a system in an inertial frame moving under the external and added external force called fictitious force, or you consider it as a system moving uniformly, accelerating uniformly. All right. So is there any way to distinguish physically between these two different situations? The answer is no. All right, this is a very important principle in the general theory of relativity. There is no way to distinguish the two scenarios. All right, so from now on, keep this in mind. A uniformly accelerating frame can be transformed into or is equivalent to an inertial frame, provided that you have added the correct fictitious force to it. All right. Okay, how about let us take 5 minutes break and then come back. Okay. Okay. All right. So a uniformly accelerating system is very simple. We can treat it as an inertial frame of reference, provided that we can add an appropriate fictitious force. Then all the physics can be, or all the procedures that we used in dealing with physical problems in non-inertial frames can be applied to such an uniformly accelerating system. All right. For example, conservation of momentum, conservation of energy, and all these, or we can define a potential energy due to the fictitious force, because we can treat it as an external gravitational force, all right? Just like a gravitational force. So there is no mystery about the uniformly accelerating system. However, a uniformly rotating system is totally different. It is intrinsically non-inertial, all right? We cannot transform away the acceleration like the uniformly accelerating system, all right? So we have to be careful when we are dealing with a uniformly rotating system. Now, the fictitious forces do not have the simple form. So we have to be careful in deriving the fictitious force. And the fictitious forces involve several terms. One of which, including one which is velocity dependent. All right. Now you must have heard about Colloidus acceleration in the introduction to physics course. Then, obviously, we know that the Coriolis force, Coriolis acceleration, depends on velocity, right? So we can expect that one part of the fictitious force must be velocity dependent as well. Okay, if a particle of mass m is accelerating at rate a with respect to inertial coordinate, and at the rate a rotational with respect to rotating acceleration, rotating coordinate, then the equation of motion in inertial frame is given by this expression, Fa equal to ma in equation 1. Now, in a rotating system, a similar equation of motion can be found, which is given in equation 2, all right? But this time, we can see that the force is replaced by F rotation, all right? A is replaced by A rotation, okay? Even though the form is the same, but all these components are different. Now, if the acceleration of the particle in the two systems are related by this expression, A is the relative acceleration between the inertial frame and the uniformly rotating frame, then the F rotation is equal to the F observed in the inertial frame plus the corresponding fictitious force, okay? And this fictitious force is equal to minus ma, just like the case of a uniformly accelerating system. However, you will come to a very important question. What is this A? Okay, this is not an easy question. So how do we derive this A? Okay, consider an inertial coordinate system x, y, z, and a coordinate system x prime, y prime, and z prime, which rotates with respect to the inertial system at angular velocity omega, all right? So we consider an arbitrary vector B, which has components Bx, By, Bz in the inertial frame. And its components are Bx prime, By prime, Bz prime with respect to the rotating frame, all right? Now, if I differentiate this vector, we want to find the rate of change of this vector, we will see that in the left frame or inertial frame, dB vector dt is given by this. On the other hand, if we perform the same operation in the rotating frame, it will be a little bit different. Okay? Why? Because the basis vectors of the rotating frame is not fixed. It is changing. All right? So when we differentiate it, when we differentiate this expression, we have two terms. The first term contains all the time derivative of the components. The second term involves the time derivative of each basis vectors. All right? Okay, so the rate of change of a vector measured in the inertial frame is equal to the sum of these two contributions observed in the rotating frame. Okay? Now, if you sit inside the rotating frame, you will measure this. Okay? If you want to communicate with another observer in the inertial frame, so we have to add this. This tells you this gives you the difference between the two measurements. All right. Now we consider a simple situation. The rotation is about the z-axis. In other words, omega vector is equal to omega. Omega is a constant pointing in the k direction, okay, z direction. So what is di prime and dt? It is the cross product of the omega vector and the I prime vector. How about the j prime? Again, the cross product between the omega vector and the j prime vector, all right? How about the time derivative of k prime vector? Again, the cross product of omega vector and the k prime vector, okay? So this second term can be summarized in this form. Okay, we put back the components. Okay, so this whole term is equal to omega cross b vector. All right, because we multiply the b prime, bx prime to here, by prime to here, bz prime to here. All right, we get back the b vector. Now, the b vector is a vector, the same vector in both inertial frame and accelerating frame. All right, so we can have a very compact form for this relation. Okay, again, two terms. The first term is dB vector dt according to the rotating frame or measured in the rotating frame. And this is the rate of change of the B vector observed in the inertial frame. What is the difference? Omega vector cross B vector. All right. So if you make the measurement in the rotating frame and you want to report it to the observer in the inertial frame, you have to add this extra term so that you both will have consistent results. In this equation, we can make two observations. The vector B is the same in both inertial and rotating frame. So that's why we drop the subscript. However, the derivative with respect to time of B are different in the two frames. All right, so that's why we have to put in the subscript. It is only the time derivative of B which depends on the coordinate system. All right, keep this in mind. Now, if we have a displacement vector and we want to find the velocity, all right, then we have to differentiate. If we want to find the acceleration, we will differentiate the velocity vector once again. Okay, so we apply the relation given here. We can see that the dv in dt equal to dv in dt rotation plus this extra term, correction term. Okay, we know that the v in, which is actually equal to dr vector dt, right, is equal to dr vector dt according to the rotating frame plus this compensation term. So we put this into equation 12, we get this. We get the equation 14, all right? So for an observer in the inertial frame, he measures this acceleration. For an observer in the rotating frame, he measures this acceleration. So the two results are different. How can we make sure that they can communicate and get consistent results? We have to add these two terms. All right, these two terms. These are two fictitious terms. Once we know the acceleration, then we can figure out the forces. So the forces observed by an observer in the rotating frame is equal to m times a rotation. And we can see that it is equal to the force observed by an observer in the left frame plus an extra term, the correction term. And we call this correction term the fictitious force, all right? So you can see that this fictitious force is much more complicated than the case, than that in the case of a uniformly accelerating system. It consists of two terms. The first term, we call it Coriolis force, which depends on the velocity dependent force. Another term, we call it centrifugal force, And this centrifugal force has a very important characteristic. It grows with the vector r. We all know that the physical forces, all the physical forces will decay to zero as we go far away, right? Say, for example, gravitational force. If the two masses are separated further and further away, the force will decay to zero. How about the electromagnetic force? Again, right, Coulomb's force. However, this centrifugal force is very different. It grows with the separation. So that's why it is not a physical force. It is a fictitious force, all right? So if we represent these forces or these terms pictorially, you can see this diagram. So it is rotating about the z-axis. This is the direction of the angular velocity. Okay. So this is the centrifugal force. This is the centrifugal force, all right, as shown here. And there's another one, the Coriolis force. Okay, let us look at this example. We have a bead slice, which slice without friction, okay, along this wire, which is rotating about this axis at constant speed omega, okay, rotating with a constant angular velocity. We want to find the force exerted by the wire on the bead. If we use the inertial frame, this is the so-called reaction, right? The reaction between the bead and also the rod. Okay, so we go to the rotating frame. When we sit on the rotating frame, what do we see? We will see that the bead is going inward and outward, am I right? Radially, along this direction. Inward, outward, inward, outward, okay, along this direction. There is no sideway motion, all right? So we have the force diagram, then we write down the equation motion. Centrifugal forces, m omega squared r equal to r double dot. The Coriolis force, which is perpendicular to the radial motion, is equal to 2mr dot omega, right? Coriolis force, equal to this normal reaction, okay? So solving the radial equation, we have r equal to a e to the power omega t and plus b e to the power minus I omega t. I think I missed the I think. Oh no, this is correct. This is correct without the I, because we don't have a minus sign here. Okay. Now, A and B are constants depending on the initial conditions. Once we find the R, we take the time derivative and put it back into this equation 18. We can obtain the normal reaction, the force acting on the bead by the rod, okay? Can you follow? All right. Now, this is your task. Can you go home and try to work out this problem in the left frame? Okay, in an inertial frame. What will happen? When you are sitting in the left frame, you will see that it is the bead is rotating, right? And also it is moving out and in along the radial direction. And you are asked to find the reaction between the rod and the bead, right? So go home and try to work out this problem in the left frame or inertial frame. In the rotating frame, you can see that it's very simple. We can get the answer very quickly. But how about in the inertial frame? All right. Okay, I think I'll stop here. Do you have any questions? Do you have any questions so far? Now, keep this in mind. A uniformly rotating frame is very different from a uniformly accelerating frame. A uniformly accelerating frame can be transformed into an inertial frame by adding an appropriate fictitious force, which you can consider to be an artificial gravitational force, all right? However, our uniformly rotating frame is a bona fide non-inertial frame. You cannot transform it back to an inertial frame. by adding appropriate fictitious force. Okay. Now, in the uniformly accelerating frame, you can, after transforming back to an inertial frame with an added fictitious force, you can apply all the procedures that you have learned with respect to inertial frames. Conservation of momentum, conservation of energy, conservation of angular momentum, whatever you like. The analysis is exactly the same, all right? But uniformly rotating frame, we are not so lucky. However, but it is very useful, especially when you want to apply to more complicated systems like rigid body motion. Okay, any questions? One, any questions? Okay. Let me do it again. Okay, equation 9. You mean this one? Okay. Forget about the rotation matrix. Think about the right-hand rule. When you have the I hat, you try to rotate it. The length of this basis vector remains the same. So, right? And what is the direction? Tangential direction. Am I right? Tangential direction. Just think about the polar coordinates. Go back to polar coordinates, then you understand. Okay, go back to polar coordinates. Okay, any more questions? No? Okay, then I see you on Thursday.